Okay, so we're doing the second part of the proof for the mid-segment theorem in example 9. And the first part we showed that MS was parallel to OL. Okay, and now we have to show that MS is a half OL. Okay, so we're going to need to use a distance formula to do that. So the distance formula, just to remind you up here, is x2 minus x1 squared plus y2 minus y1 squared. Okay, so we've got that for the distance formula. And so now we have to, so let's do that for OL. Now, some of you already know what the length of OL is, a real fast way, and that's fine. I'm still going to do it the long way with the distance formula, and then I'll go back, for those who didn't realize it, explain it the fast way. So I'm going to do OL in orange. So I'm going to call this x1, y1, x2, y2. And we know OL, subtract the x's and then square it, subtract the y's and square it. So when you subtract the x's, you get a minus 0. When you subtract the y's, you get 0 minus 0. Oh, that's nice. Good night, Irene, there. And this becomes the square root of a all squared, which means OL equals a. So I'm going to write that up here. OL equals a. It's important that we have that. So it's a good result. Now, you could have gotten that really easily without using the distance formula. All you did was move in the horizontal direction a units because we started at 0. So that means the length is a. You didn't move up, so you don't have to worry about using Pythagorean theorem. Just count the spaces. So you still would have gotten OL as a. So I'm going to erase some of that writing. Okay, and you may, if you're writing the work down, you still have it written down for OL with a distance formula, you should pause it now. Now the other distance that we need is MS, and then we can compare it. MS is right here. And some of you might be able to get that answer really quickly. Again, I'm going to go through the distance formula to show that it works. And so MS, well, we'll call this x1, y1, x2, y2. And we get MS equals the square root. I'm going to do the x's first. So I'm going to have a minus sign. I'm going to have x2a plus b divided by 2. x1 is b divided by 2. And I don't have room to put the y's, so I'm going to put them underneath. Remember, they're still under the square root. Okay? And it turns out they're the same. C over 2, C over 2, which means if they're the same, then this is going to end up being 0 squared. 0 squared is 0. Add 0 to this part here in the x, and you still have that part. So we only really care about this here under the square root because this part is gone. Now let's look at that, and we notice here it has a 2 on the denominator and a 2 in the denominator. They're the same. So all we have to really do is put the numerators together and simplify. So I'm going to write that down. So I'm going to get MS equals the square root of a plus b minus b all over 2, because they all have the same denominator, squared. Don't freak out. We're going to get there. Well, again, these will cancel out and give you 0. So I'm left with a over 2 squared, which means MS is, if you split it up, a squared over 2 squared, which is the square root of a squared over the square root of 2 squared. And remember what happens when you square and square root? They cancel out, and you're left with A over 2. So we really now know that MS, you could say, is A divided by 2 or 1/2 A, same thing. And remember what A is? If we use the substitution, property of equality, we can now take wherever we see A, we can now put OL. Okay, so we're going to get MS equals 1/2 OL, which is what we tried to show right here. So we're very happy. We have just proven that the midsegment, MS, is half the length of the bottom side of the triangle O to L.